All right, how's it going, class? It is Saturday, 1 p.m. for me right now. Um, this is take two on this video. I don't know, luckily I only got about a minute in before I realized I was muted, but let's try this again. We're simplifying each trigonometric expression. That just means take a complicated trig expression and, well, make it simpler. We'll apply the identities we've got, which are not that many. We've got reciprocal identities and quotient identities and Pythagorean identities. And I hesitate to even list the co-function identities because frankly, they're not going to come up. At least not on this homework. I reserve the right to bring them up later, I suppose. But looking here, cosine squared is going to stay cosine squared. My general rule of thumb, if you recall, was anything that can be turned into sine or cosine should be turned into sine or cosine. If you can boil everything down to sort of common factors, common terms, then you're going to see what factors can combine, what factors can cancel. And that's sort of the heart of simplifying, right? Is to take multiple things and combine them or get them to cancel out. So that's a really good idea. So tan squared becomes sine squared over cosine squared, at which point it becomes pretty darned obvious that the cosines can cancel. If you think of this cosine as being over 1, then we've got cosine squared factors that can be cross-reduced. That leaves us with simply sine squared. All right, now though, the restrictions. Sine squared is an expression whose domain is real numbers. So this thing here has no restrictions on its domain whatsoever, but this thing does because it contains a tangent. And tangent does have asymptotes in its graph. We know that. A cleaner way to think about it, though, is if tangent is sine over cosine, then we can't let cosine be 0, or else we'll have division by 0 will be undefined. So one way to stipulate your restrictions is just to say, hey, cosine of x cannot be 0. But that's not really what I'm after. I want you to give the actual restrictions on the angle measure. So tell me what x can't be. And for that, we're just going back to the unit circle like we did last week and the week before. And if cosine is the x, then x will be 0 here and here. So that's telling you that x cannot be pi over 2 plus pi k. And that's it. So those would be the restrictions that we need to place on this function. This guy's domain's all reals. That's not okay. We need this thing's domain to be the same as the domain of our original expression. So we'll say, comma, x cannot equal pi over 2 plus pi k, where k is an element of the set of integers. What you're doing when you do that is you're making these functions actually equivalent to each other. This expression here has restrictions on its domain. Sine squared doesn't, unless you put them there yourself. That's why we're calling these restrictions. We're not saying give the domain. If you gave the domain would be all reals. You're placing restrictions on this guy's domain so that the domain is the same. Okay, I've explained that a bunch of times. It's never going to get any better, I don't think. That's the best I can do, so I hope you're with me. Let's try another. Yeah, let's try another in a second. Okay, I'm back, and I am going to take one more crack at explaining the restrictions thing. So to do it, we're going to go to everyone's favorite, Desmos. So if you take a look, I've graphed the original expression, right? Cosine squared of x times tangent squared of x. And if you graph it, you get this graph here. It basically looks just like the graph of like sine and cosine, but we know that it isn't because it runs from 0 to 1 instead of from -1 to 1. So it's a slightly different graph. Now, if you just graph it, it looks fine. It looks completely continuous, but I've added holes because we know they ought to be there. And just to prove that, I made a table that shows you that at -pi/2, this function is undefined. That's because tangent is undefined at -pi/2, also pi/2, also 3pi/2. So these holes should all be there, right? But now, if I turn that function off, turn the holes off too. and you turn on sine squared, our simplified version, you see the holes are not there anymore. And even in our table of values, they're not there anymore either, because tan squared is gone now. So that factor that used to cause our discontinuities isn't there anymore. And this is another way just to sort of prove that sine squared is not truly equivalent to cosine squared times tangent squared, because cosine squared times tangent squared is a graph that has holes in it. And the graph of sine squared is a graph that doesn't have holes in it. So if we want to write an expression that's truly equivalent to the original, we need those holes to be there. And the only way to get those holes to be there is to, you guessed it, put them there yourself, right? You have to literally pluck all of those x values out yourself. Say, nope, you're bad, you're bad, you're bad. And so you're basically plucking little holes in the graph that you know are supposed to be there. That's my last crack at trying to understand the restrictions thing, okay? Now let's just keep going. Let's make sure we know all the algebra skills we need to actually simplify these expressions down all the way. So looking at number 2, we talked about the Pythagorean identities. We knew that the most basic one was, dang it, sine squared plus cosine squared equals 1. And then I told you to also be familiar with a whole bunch of other alternate forms. The alternate forms were, that you could flip this around. You could obviously do cosine squared plus sine squared. I'd like to think that's pretty trivial. You could also subtract cosine squared, though, and find that sine squared of x is equal to 1 minus cosine squared x. That's semi-non-trivial. But if you stop and think about the fact that all that you're doing is subtracting something from both sides, that's pretty damn trivial. But looking up here, you see 1 minus sine squared. So that means from this first equation, I'm just subtracting sine squared. So cosine squared x is 1 minus sine squared. That's an alternate form of the Pythagorean identity. That means all this stuff in parentheses here, you can literally just substitute in cosine squared. You can do that right away. It's justified by the Pythagorean identity. So this is now cosine squared x times cotangent x. Now we can make some changes. This is cosine squared x times cosine x over sine x. And we don't get that satisfying elimination of factors here, but we do get to combine factors. So we land on cosine cubed over sine. And so you could give that as your answer. And we talked a bunch in class about how maybe this isn't the simplest form. This still contains a fraction. We like to eliminate fractions when we can. This has a greatest power of 3. We like to keep the powers as low as possible. So maybe actually going back to the form where we have a cosine squared times a cotangent, you can make a pretty strong case that that's actually better and simpler. There's no fraction here, and the greatest power is 2 instead of 3. So this blue answer might be the better answer. So Ms. Butler and I had a chit chat specifically about this very problem, and we both agreed that no one can make a case that one of these is better than the other. So frankly, what that means is no question like this will appear on your quiz. You'll have questions like number 1, where it's inarguable that the best form of this would be sine squared. Nobody could reasonably find any other way to express this that is better. And so that's what the questions on your quiz will be like. There'll be some final stopping point that is very clearly the end of the line. So anyway, I would take either of these. I don't care which, but I do need restrictions, or do I? I don't think I do actually, because what's the domain of the original? The 1 is obviously fine. Sine is all real numbers. Cotan has zeros. It's undefined. It's undefined when the denominator is 0. So basically cotan just says, hey, sine cannot be 0. But this function is obviously undefined when sine is 0 already. We already know that. So I don't need to put a new restriction on top of that. And same thing here. Cotangent still has the same restrictions. So in my understanding, since this expression has the same domain as the original already, I don't need to add any new restrictions. So rather than saying list any restrictions, I'm going to say extra restrictions. And then say none. I don't need anything new beyond the domain that this thing already has. Ms. Butler and I do agree on that, and I don't care. I'm standing firm on what I say. I say when we talk about restrictions, we're talking about extra. We're talking about above and beyond the domain already. That's my stance, and I'm sticking to it. Let's move on to number 3. So that's a little small. It's not a hell of a lot better. That's okay. All right. So this is just a product of 3 things. I would take my own advice, turn everything into tangent. Turn everything into sine and cosine. So this is sine squared x over cosine squared x. Cosecant is 1 over sine squared. And cosine is obviously just cosine over 1. Now we can start canceling. The sine squareds cancel. And even the cosine definitely cancels 1 of the cosine. So we now just have 1 over cosine, which becomes secant. So this is another example of a great problem to actually put on the quiz, because clearly this is the best outcome, secant x. There's no better form. That's the best. Now, what are the restrictions on my original? What would its domain be? Well, because it involves a tangent, and because tangent is sine over cosine, we know that for the sake of that factor, cosine cannot be 0. But cosecant is 1 over sine, so we know that for the sake of that factor, sine cannot be 0. And then cosine, he doesn't care. Cosine's got a domain of R reals. So looking at this, my original expression would need restrictions when cosine is 0, that's here and here. It also needs restrictions when sine is 0, that's here and here. So basically all 4 quadrantal angles are out of this guy's domain. Down here though, we only have secant. Secant's 1 over cosine. So it's only cosine that's been restricted from this guy's domain. So thinking about this, the only restrictions that we already have are when cosine is 0. That's here and here. That means if I want to make these things the same, then on my own, I need to pluck out these 2 locations, right? So for me, the restrictions that go above and beyond the values of x that are already naturally removed from this guy's domain are just these guys here. So that would be 0 plus pi times k. So 0 plus pi k is just pi k. So again, I'm not saying that's the domain. If you were going to list the domain would be our real numbers, comma, x cannot equal any of these 4 positions. That would be 0 plus pi over 2, pi over 2, pi over 2, pi over 2, pi over 2. So pi over 2k. So the domain is that. But I'm saying the only restrictions we need are these. You need to pluck out the greens because the blacks are already gone. The blacks were never in this guy's domain anyway. So they're handled. You got to handle the greens. All right, I'm going to stop explaining that, I promise. All right, let's do 4. So for number 4, all right, I'm going to do this the long way, then I'm going to do it the easy way. The long way, of course, is to keep on doing that thing where you turn everything into sine and cosine. So tangent becomes sine x over cosine x. Cotan becomes cosine of x over sine of x. Tangent is sine of x over cosine of x. Then once everything's been boiled down to sines and cosines, you'd take this guy, distribute it in. And you would notice that when you distribute this in, the sines cancel, the cosines cancel, you just get 1. But that's the point where I hope your brain goes, oopsie daisy. Obviously, tangent times cotangent would be 1. Tangent and cotangent are reciprocal functions. We know that cotangent is 1 over tangent. So tangent times 1 over tangent will always be 1. You may want to keep that in the back of your mind that, you know, if you are ever doing sine times cosecant, it would be nice if you remember that cosecant is 1 over sine. So there's no reason to jump through hoops to show work and justify this. You know right away that sine times cosecant is going to be 1 because they are reciprocal functions. They'll always give 1 when you multiply them. And just for the sake of completeness, obviously that means cosine times secant will always be 1 because they're reciprocals. Perhaps we should have listed that as alternate forms of the reciprocal identities. But there you go. Anyway, that means when I distribute this, I guess I'm going to do it the long way and say that gives me sine squared over cosine squared. So that becomes 1 plus tan squared. And now you see how we could have very easily quickly gotten there by just distributing tan. Tan times this make 1, tan times this make tan squared. We could get there in like one step. All right, so I'm not going to do that the short way a second time. We're there. We're not done though. I see a 1 and I see a trig function that's being squared. That's got me thinking Pythagorean identity. If I don't have it memorized yet, then maybe off to the side, I'm thinking, all right, sine squared, cosine squared equals 1. I got a tangent here, tangent sine over cosine. So to get tangent worked into this equation, I got to be dividing by cosine squared. So then the sine squared over cosine squared, there's my tan squared. Here comes my plus 1 from cosine plus cosine. And it equals 1 over cosine squared, so that's secant squared. So lo and behold, very quickly on the fly, you can find that 1 plus tan squared is secant squared. And we are now as simplified as possible. Again, remember, secant squared will always be considered simpler than this because here it's a binomial. We've got 1 plus tan squared. That's 2 terms. This is only 1 term. That is better. So that's one of our rules. All right, do I need restrictions? I'm thinking I do, because again, we've got an expression that involves tangent. Tangent will be undefined when cosine is 0. Cotangent will be undefined when sine is 0. So again, we have both of those restrictions. Our original function is undefined for for angles that are in either of those 4 positions. But secant being 1 over cosine means again that the only restrictions we have naturally are here and here. So just like the previous problem, number 3, the restrictions would be these 2 positions. We need to tell our audience that those x values are not okay. Otherwise, our audience would think that only these values are not okay. So restrictions. And they're literally just the same as the last problem. Number 5. Small. All right. So what's tangent? Sine over cosine? Okay, I guess that's what we're doing. So we have sine x times sine x over cosine x plus cosine x. We could put this over 1. We see that if we multiply that out, we'll have sine squared x over cosine. Now, we're trying to add a fraction to not a fraction. So throw that over 1. And remember that if you want to add fractions, which we do, anytime we've got a binomial, or really anytime we have more than one term, we're looking for terms that we can combine because we're trying to simplify. So the fewer terms we have, the better. So my common denominator would be cosine, which means I would have to multiply this term by cosine x over cosine x. So by doing that, I can now bring down sine squared x over cosine. And then this will be cosine squared over cosine. And hopefully you guys remember the rules for adding fractions, which is you add the numerators. And of course, you don't change the denominator. If the common denominator is cosine, then it stays cosine. So don't go turning that into 2 cosine x or anything like that. Surely don't turn it into cosine squared. Anyway, guess what sine squared plus cosine squared is based on the most basic Pythagorean identity? It's 1. So we now have 1 over cosine, which of course is secant. So that's our simplest possible form. Have we lost any restrictions on the domain of the original? Well, sine had a domain of all reals, cosine had a domain of all reals, but tangent, since tangent is sine over cosine, tangent will be undefined whenever cosine is 0. So those would be the only restrictions on the domain of the original function. But we already have those same restrictions down here. Secant is 1 over cosine. So we already know that cosine cannot be 0. So in my opinion, there are no new restrictions that need to be placed on this. We have not lost any of those restrictions. So no restrictions needed. Period. Okay, number 6. Yeah, okay. So the temptation would be turn everything into sine and cosine, distribute the cotan. You don't want to do any of that because you should see the secant squared minus 1 and immediately be thinking about how that's a Pythagorean identity. A second ago, not a second ago, a while ago. Feels like a long time. Yeah, actually it wasn't long ago at all. We started off with our Pythagorean identity, the basic one. We divided through by cosine squared and found that tan squared plus 1 is secant squared. So we then said that we would subtract, no, we didn't have to do anything. We had tan squared plus 1 was secant. But if you subtract 1 from both sides, we see that secant squared minus 1 is tan squared. And I think that's what we have right now. We have a secant squared minus 1. So it'd be nice if we right away noticed that that just becomes tan squared. Especially because now, you may recall, cotangent is 1 over tangent. And we're now multiplying that by tan squared. So that means we can cross reduce this one tangent with one of these tangents. I don't know why I put an X down there. That's my bad. That's a 1. And then we see we're left with just tangent of X over 1, which is tangent of X. So that's the end of the road. If anyone was thinking they should give their final answer as sine over cosine. Remember, one of our rules said that you want to use the fewest trig functions possible. So you're never going to turn just tangent into sine and also cosine. That's 2 trig functions. Tangent is only 1. We also had a rule that said not a fraction is better than a fraction. So tangent is certainly better than sine over cosine. Have we lost any restrictions from our domain? Let's see. Cotangent is cosine over sine, right? So cotangent will be undefined when sine is equal to 0. Secant squared is 1 over cosine. So that means we've got another original expression that's undefined under both of these conditions. But our new expression is only undefined under the condition where cosine is 0. Tangent sine over cosine. So this function is totally happy if sine is equal to 0. But the original wasn't. So we got to go ahead now and stipulate that sine cannot equal 0. And of course, the unit circle tells us that sine equals 0 here and here. So that's pi k. So there's your simplified expression with restrictions. Moving on. I don't know how many more of these I can do. I'm going to have to head out of here in a minute. You're going to get another 2-part video, it sounds like. Because how many of these are? Oh, I'm halfway done. I'll do these 2, but then I'm going to call it quits until later tonight. All right, so here, I'm not sure what I want to do. Should I clean up what's in parentheses first and then distribute, or should I distribute right away? I'm not sure. It kind of depends. Tangent is what? Sine over cosine? What is secant? 1 over cosine? So distributing that in will turn this first term into a 1. It'll turn this into, yeah, okay. I think I would distribute it. It doesn't really matter. I think we can even do the whole sine cosine thing. So let's turn this into 1 over cosine. This is cosine over 1. This is sine of x times sine of x over cosine of x. So yeah, I think doing this is good. It's going to give you a better chance to see what the heck's going on. But when we take this and distribute it in, we're obviously getting cosine over cosine, which is simply 1. When I distribute this in, we're going to have sine squared in the numerator and cosine squared in the denominator. That's going to be tan squared, but I'm going to show it slowly. We'll show the sine squared first, cosine squared. And then we'll go ahead and apply the quotient rule to turn that into tan squared. And you hopefully recall this is equivalent to secant squared. So we're definitely done simplifying. Do we need restrictions? Let's see. I see a secant. That obviously will have the same restrictions as secant squared. Cosine has no restrictions. Sine has no restrictions, but tangent does. Tangent is sine over cosine. So the only restrictions tangent has are the same restrictions as secant. Secant's 1 over cosine. So secant says, don't let cosine be 0. Tangent sine over cosine. So tangent says, don't let cosine be 0. So those are the only restrictions. And this still has those same restrictions. So no further restrictions are necessary. I spelled necessary right? It's always been a hard one for me. All right, I said I would do 8, so I'll do 8. All right. I guess let's do the whole change it all to sine and cosine, see what we're working with. This is 1 over sine minus sine over 1 multiplied by 1 over cosine squared. So distributing that in doesn't feel terribly useful, does it? If you distribute that in, you'll just have 1 over sine x times cosine squared x. Doesn't seem good. So it seems like we'd want to simplify the binomial first. So to do that, we're going to need common denominator. So you'll be looking at 1 over sine x minus. You're going to hit this with a sine over sine. So you're going to suddenly have sine squared in your numerator over sine. This can stay 1 over cosine squared, or you can turn it back into secant for the moment. I don't care. But now when you combine these fractions, you've got 1 minus sine squared, which is ringing some pretty loud Pythagorean identity bells in your head, I hope. One minus sine squared is cosine squared. So you're looking at a cosine squared x over sine x multiplied by a 1 over cosine squared x. So they can now happily be canceled out. You now just have 1 over sine, which you know to be cosecant. So that's the end of the road on that. And again, we've got a cosecant up here already. So obviously the restrictions that that term gives us are going to be the same restrictions we have down here already. Secant is 1 over sine. So this is saying sine better never be 0. Sine has a domain of R reals, so that doesn't matter. But secant is 1 over cosine. So this is telling us that cosine cannot be 0. And you can see that we've lost that restriction through the process of simplifying. When we canceled out these cosines, we've now lost the fact that cosine can't be 0. So we need to add that idea back in. We don't have to stipulate that sine can't be 0. Again, that is already addressed in the function here. Those values were never in our domain anyway. The ones we're concerned with are the ones that we lost. So when is cosine 0? Cosine is x, so cosine is 0 here and here. So again, it's pi over 2 plus pi k. So our restrictions are: tell your audience that x may not be pi over 2 plus pi k. There you go. I will finish the rest later, I promise. Right now my head hurts. And my kids are up from their nap, so I have to stop. But I'll come back to you. Adios.